Now I would like all of you to solve this problem and let me know what is the answer to this problem. I think solution to this problem is quite straightforward. I have 12,000 units per year and a year is 50 weeks. I need this 50 weeks because the flow time is stated in terms of weeks. I cannot have throughput in terms of year and flow time in terms of week. I can write it like this and transform throughput into weeks, or alternatively, I could have 3 divided by 50 and transform 3 weeks into a year. Therefore, I can do this and then multiply it by 12,000, or I can do this and multiply it by 3. In one of them, I transformed throughput per week and left 3 weeks as week. In the other one, I transformed week into a year and then multiplied in throughput per year. Both of them are correct. And if I do the math, in both situations, I end up with 720, and that is my inventory. Correct? So on average, there are 720 flow units inside the system. Correct? Throughput, 12,000 divided by 50, which is 240. Claims per week. R times T is equal to I. Throughput is 240. T is 3. Therefore, there are 720 claims waiting. Any question? Now, try to solve this part. Let's see what is the situation here. Inventory of cars is 300. We see it here, right? It is 300. Throughput of car is 50% of the overall throughput. Overall throughput was 240. 50% of 240 is 120. Now the rest of the problem is a piece of cake. Out of 3 components of the Liddell's law, we do have 2 components. We put it into the equation and we will get the answer. T times 120, which is R, equal to inventory, which is 300. Solve the problem. 2.5. 2.5 what? 2.5 weeks. Why weeks? Because this 120 was in terms of week. If we would have used the yearly throughput, then the number we would have got here was in terms of year. So pictorial representation of the problem is like this. 240 claims per week come in. They go into these 4 rivers. At what rate? At these rates. 50%, 10%, 10%, and if I have these 3, finding this one is quite easy because 1 minus these 3 will become this one. And because summation of these 3 is 70%, so this one is 30%. Look at it like a river. It's a main river, 240 cubic meter per minute is passing it, then it will become 4 different rivers. Then associated with each river, there is a dam. The depth of a dam, the volume of a dam does not depend on the flow of the river. It depends how much space do you have. It depends on how slow or fast you process the flow units. It is possible that 100 per hour come to your office and you have enough people and you can handle all 100 of them, right? So on average, you will have a small inventory, but maybe 100 per hour come over there and you can only handle 20 of them per hour. Then you have significant inventory. So these are throughputs. When I multiply 240 by these percentages, these are the numbers I get. Then we also have inventories in each of those places. We have 300 here, 114 here, 9 here, but in our previous computation, we realized that a total of 720 is inside this system. So if I subtract those numbers from 720, I will get the inventory for house insurance. As soon as we get the concept of the Liddell's law, and as soon as we understand that throughput is like a river and inventory is like a dam, throughput depends on per hour, per minute, per day, per month, per year. But inventory is a number which is always there. Then the rest of the problem is a piece of cake. Maybe sometime we need to do a little bit computations. And maybe those computations sometimes are a little bit difficult, but they don't have anything with the Liddell's law. Because as soon as we prepare the two of the three components for the Liddell's law, the third one can be computed easily. So in this case, average number of claims was 720. If I subtract 300 from 720, 114 and 90, the rest is 216. Therefore, inventory in house insurance is 214 and throughput is 30% of 240. 30% of 240 is 72 and inventory is 216. Therefore, the flow time for house insurance claims is 3 weeks. The problem that we solved is exactly like this problem, correct? So I would like you to quickly go through this problem and solve this one too. It is exactly the same as the other one. Mathematically speaking, they are exactly the same, but physical instantiation are different. On average, how many accounting majors get graduated each year? That is quite simple because total is 1600, correct? 25% accounting major, right? Then the rest is a piece of cake. 25% times 1600, 400 per year, right? What about this one? That is also quite simple. 15% finance. 10% of 1600 is 160. 5% of 1600 is 80. So 160 plus 80, that would be 240. On average, how long does it take a student in this college to get graduate? So I need to find the overall inventory in this college, and that is 9,000. I don't need to even compute it, right? And then 1,600 students per year coming, correct? Therefore, this one is what? Throughput, correct? And this one is inventory, correct? And our question is, how long does it take for a person to get graduated? And throughput times flow time is equal to inventory. Therefore, flow time is equal to inventory divided by throughput, and inventory is 9,000 and throughput is 1,600, 5.625. So on average, it takes more than 5.5 years for a person to get graduated in this college. Therefore, the Little's Law is applied on components of the system as well as on the total system, right? The rest of the computation is simple. This is percentage of throughput. So we multiply each one of them by 1,600 and we will get these numbers, where the summation is equal to 1,600. Inventory we had and the summation is 9,000. We said 9,000 divided by 1,600 is 5.625. We can do the same thing for all components here. I divided by R, 7.5. I divided by R, 6.25. So accounting people spend more than any other student in this college, and finance people, but this is an example. I don't know if this is correct about accounting and finance, but this is an example I have built to create another example exactly the same as the insurance example that we solved, and say as long as the substance, mathematical substance of the problems are similar, we can just do the same thing on both of them, right?